Hello everyone, today we'll talk about how to use coordinate systems in practice, what they're good for. This is material from 4.4. So just recall from last time, suppose B is B1 through BP is a basis for a vector space V, and X is in V. We have this vector, the B coordinate vector, which is, let's say, C1 through CP, where, remember, those C1 through CP were the weights in this unique linear combination that gives you X. So if I have a basis, there's one and only one way to write a vector X as a linear combination, and those weights go into a vector called the B coordinate vector. Okay, and so we think of this, we talked about this last time, or maybe 2 times ago, think of this as defining a linear transformation. Well, it's going to be linear, maybe it's not so obvious yet, but this is a transformation from V to RP, taking the vector X to the vector XB. And this is a vector with just, this is just a vector of numbers because it's weights of a linear combination. So it turns out, here's a theorem, that this transformation is a linear transformation and is 1-to-1 and onto. Okay, so these are features, properties of a transformation we talked about last time. Remember, linear means that it preserves the operations of addition and scaling. 1-to-1 means that there's at most one vector that gets sent to any vector. So here's my cartoon that V is getting mapped to RP here, right? So I'm taking a vector X, which you think of as this is an abstract thing now. And X is getting mapped to, a legit vector now in RP. This is what we call XB. Okay? And what's kind of nice is that, this is the world, this might be the world of polynomials or some other abstract vector space, but it's giving me a vector in RP that I can then work with. It's a list of numbers that we then have tools to understand. So this transformation is linear and 1-to-1 and onto. So this is what's called an isomorphism of vector spaces. And loosely speaking, what this does, it allows us to think of properties in V, for example, linear independence, span, etc., in terms of their counterparts in RP. All right, so if you give me a bunch of vectors, for instance, in V, and I want to know are they linearly independent, I can map them over to RP and then use my tools that I have over there to answer such a question. So let me give you an example. So e.g., if I was looking at, let's consider the vector space, I don't know, P2. So this was P2 was the polynomials of degree at most 2. This has a basis, we talked about this before, this has a basis consisting of 1t and t squared, because any polynomial of degree at most 2 can be written as something times 1 times something plus something times t plus something times t squared. This is what we call the standard basis for P2. Note actually that P2 then therefore has dimension 3, right? It's not 2, but it's because you've got these constant polynomials to worry about, that you have 3 elements in a basis, therefore this guy has dimension 3. Now, let's consider the set 1 plus 2t squared, that's a vector in RP, 4 plus t plus 5t squared, that's a vector in P2. And then 3 plus 2t. Okay? So these are all vectors. This is a set of vectors in P2. And I want to know, is the set linearly independent or not? Okay? So what I'm going to do here is what we talked about last time, that I'm going to think about the world of polynomials, this P2 world, and I'm going to take the image in R3 by taking coordinate basis vectors. So for instance, 1 plus 2t squared, well, what is that in terms of the basis, right? This is 1 times 1 plus 0 times t plus 2 times t squared. So therefore, this gets sent to the vector 1, 0, 2. Makes sense? Because it's one of the first basis vector. Remember, here are my basis vectors. These three here in that order. It's 1 of the first, 0 of the second, 2 of the third. And of course, 4 plus t plus 5t squared gets sent to 4, 1, 5. And then lastly, 3 plus 2t gets sent to what? 3, 2, 0. Okay? And now the idea is that I've taken those three vectors, these kind of abstract polynomials over here, and I've now realized them as three vectors in R3. So now we can consider the set 1, 0, 2, 4, 1, 5, and 3, 2, 0. And I want to know, in R3, are these things linearly independent? Well, that's what we've been doing this whole semester, right? So what I do is I take these three. I can now make a matrix. So let's consider the matrix. This is what we've been doing all semester. I can now consider the matrix 1, 0, 2, 4, 1, 5, 3, 2, 0. And what do? Well, you row reduce because I want to know where the pivots are, the usual story. Well, let's see. So I've got the first pivot here. Let me clear below it. So this will be 0, 1, 2. And then if I take minus 2 of that first row, it's minus 3, minus 6, which then, clearing below this pivot, becomes 1, 4, 3, 0, 1, 2. Looks like 0, 0, 0. So in fact, I only have two pivots. I'm missing a pivot in column 3. Therefore, the set here is linearly dependent, which means the original set was also dependent, actually. So this was actually a set is linearly dependent. Okay, so that's the kind of thing you can do. I think I'll stop there. We'll do some more examples maybe on the worksheet, but this is the reason why we think of bases is that one nice feature is that, as we've seen here, we can think of abstract vector spaces in terms of properties of Rn. We can think about these vectors in this abstract vector space. Once we have a basis for the abstract vector space, we can then take their coordinate vectors, living in this case in R3, and then apply our usual methods that we've learned to love. So we'll see you next time. Thanks.